Hi everybody, my name is Gabriel Oliveira, and today I will present my undergrad work titled Outflows in Active Galactic Nuclei of Nearby Galaxies. So, at first, what are Active Galactic Nuclei, or AGNs? So, AGNs are one of the most energetic phenomena that occurs in our universe. They present very high luminosity compared with other normal galaxies that doesn't have the AGN that can be attributed just to star emission. So what is actually happening in the center of galaxy is that we have a supermassive black hole that are accreting matter. So when this happens, this produces a lot of light and a lot of energy. And it has a characteristic emission that differs from the star emission. Okay. Just for information, there is a classification to each AGN according to the orientation that we see each one in the sky. So when we look from the determined orientation, we can see a blazar, a radio loud quasar, a broad-line radio galaxy, SAFER1, SAFER2. Okay. Second, what are outflows? Outflows are winds or relativistic jets that are produced by the accretion disk of the AGN. The winds are from radiation pressure, and the relativistic jets are produced from the plasma magnetic fields that are produced by the accretion disk. So, because the high energy that are produced in the phenomena, the gas present in the galaxy are excited and ionized. So we can see different phases of the same gas or same atoms that we are looking in the galaxy. Outflows are one of the fundamental mechanisms by which the central supermassive black hole interacts with its surroundings and with the galaxy as a whole, which is called feedback. Feedback is a necessary mechanism to understand the evolution of the galaxy. In the picture, I showed the two kinds of winds that we can observe. The first one is mechanical. This one here, mechanical. So the gas by momentum transfer move away the surrounding gas of the black hole. And the second one is a thermic one. So because the high energy produced, the gas around the black hole are heated up, and then it expands. And so we have a wave of gas that are pushed away the reminiscent gas that are present in the galaxies. Okay. So next, how we study outflows? We use spectroscopy. So when the gas in the galaxy are excited by the AGN, it produces emission lines on the electromagnetic spectrum. So here we have two light emissions, this one and this one. And here are illustration on how the light emissions are produced. So we can measure the gas velocity and the gas dispersion by quantifying the shift in the emission lines of the spectrum caused by Doppler effect of light. Like when we hear the sound of ambulance, when it's going towards us and moving away from us, we can observe the same phenomena with light. And when the gas emits his light, due to its velocity, if it is approaching us, we can see the light becoming more blue and when the gas is moving away from us, we will observe the light produced by it, or red. Okay. So we can measure the velocity from this shift that we observe in the emission lines. If you apply this analysis for every bit of the galaxy, for every spatial part of the galaxy, we can draw a velocity map of the gas and analyze how they are behaving in the galaxy. Okay. Here is the galaxy that was studied in my undergrad work. Here is the visible. Here is the galaxy in the visible light, and here are the maps that are associated with this galaxy. Here for a specific gas, and for comparison are the light from the stars. I will explain this plot later. So, how we detect outflows from this the spectroscopy? When outflows occur, they change the emission line profile because they increase the dispersion velocity dispersion of the gas. So, when we have gas pushing away the remanescent gas of the galaxy, we tend to generate turbulence. So, when we observe the velocity of the gas when we have outflows, we tend to observe more turbulent gas, and the dispersion, the pace of the line emission tends to become broader. So by separating the spectrum in different components, we can isolate and study different behaviors of the gas in the galaxy. So we can separate the gas that are following the rotation of the galaxy and observe the gas that are not following this movement and call them outflows. Here is how we separate this component. So the one that most match the Gaussian profile are the one that is associated with the galaxy movement, and the others that tends to be more broad are associated with the outflows. Okay, so here we have here we have the emission of light, emission of the stars, just to characterize. So here is the disk of the galaxy. You can compare this to this image. Okay, they match in orientation, and here we can see the velocity map of the star. So here we can see that this portion of stars are approaching, are moving away from us, and this portion here are going towards us. So here we have the two components that were mentioned. For this part, we have the component that follow the galaxy movement. So we can see that the pattern is likewise similar, but here we have a component that doesn't have this pattern and are associated with the outflow. So all these gases that are separated with, from this one are moving towards us. So we characterize them as outflows. Why is it so important that we study outflows? When we study cosmology and when we study the evolution of the universe and ignore this kind of phenomena, the Earth feedback and all the effect that they can cause on the galaxies, we obtain galaxies with a lot of extra stars. So galaxies are more blue or more brilliant because they have a lot of stars. And when we consider this, and when you observe the actual universe, we have much less stars than just from the theoretical cosmological universe evoluted. So we need this kind of phenomenon to match our understanding of the parameters of universe and how galaxies actually work. So when this kind of phenomenon occurs in a galaxy, they suppress the formation of stars. And when we see in the present the galaxies, we see them with much less stars than the theoretical revision.